Hey folks, welcome back to our next pre-calc lesson. So today we're going to be having a blast from the past. You've seen it in geometry with using trig to find sides and angles of right triangle problems. And you've also seen this in geometry where we're using our inverse trig functions to do so. So by the end of this you're going to know a lot more trig functions. And after this, your next class is going to be a journal problem. So you can definitely add this to your journal then. I would also really start studying because a week from this Tuesday, you're going to have an exam. So start studying, folks, so that way you can do fantastic on that exam. But hey, enough about the future. Let's focus on the present, and let's deal with finding sides and angles in right triangle problems. Inverse trig functions are the inverse of the original trig functions. They undo it. So instead of returning a ratio, like sine, cosine, and tangent, we'll always just return a ratio of two sides together. Inverse trig functions are going to return an angle, and we can use them for a bunch of great ideas. Now, a bit about notation. This is not the same thing as this. Reason being, this is the inverse. All it means is that it would undo cosine. This is equal to 1 over cosine of x. It's a bit annoying because we're using the exponent of -1 in both cases. However, up here, because the exponent is right next to the cosine, we're going to use that to refer to the inverse. Now, down here you just have our three examples. Sine of x is undone by sine inverse of x. Cosine of x is undone by cosine inverse of x. Tangent of x is undone by tangent inverse of x. And you'll notice that these are just the three original functions. They have nothing to do with the reciprocal functions. And there's a reason why. So we won't use an inverse function for secant of x, cosecant of x, or cotangent of x. Instead, we're going to write the reciprocal functions out as reciprocals of their original trig functions. And then we're going to proceed from there. So any problem in which you find yourself having to find the inverse of secant, remember, secant is 1 over cosine of x. Cosecant is 1 over sine of x. And then cotangent is 1 over tangent of x, or you could just write it as cosine of x over sine of x. Either way, you're able to then use the inverse functions. And let's take a look at an example. Now, here, pretty straightforward example. We're just asked to find cosecant inverse of 3.2. You can also see this written as cosecant inverse 3.2. Again, the parentheses don't matter. So what we're going to do is we're going to first set it equal to an unknown. Here I'm using theta as my unknown. Reason being is I know that this is going to be an angle. So what I want to do is then I can say apply cosecant to both sides. 3.2. Reason I'm doing that is I don't know how inverse cosecant relates to original trig functions, but I do know cosecant easily relates to original trig functions. Well, I know that cosecant is just 1 over sine of 3.2. When I want to get theta by itself, so first I'm going to flip everything. Then I'm just going to apply inverse sine to both sides. And then I'm just going to plug it into my calculator. Notice I'm using the equal sign here to denote I'm getting an exact answer. And even though this is not going to end in your calculator, I can denote it's an exact answer by putting these ellipses. This is an ellipse, it's 3 dots. Alternatively, you could round, and then you just use the approximation sign. This is about 18.2 degrees. Desmos' scientific calculator to find these. I mean, I'm using the calculator a lot. It's a really good idea to show you how to do it. This link will be on your Google Classroom page. So I needed to find sine inverse of 1 over 3.2. Well, I can go over to Desmos, desmos.com/scientific, It's the scientific calculator instead of the graphing calculator. Now over here, you start off on main. I'm going to go over to func for function, and also because it's funky. Click this one, 1 over 3.2. And I get my 18.2 blah, 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 blah. You'll notice it's in degree by default, so that's always a good idea. Heck, even if you want to, you could round. You could round the whole thing if you wanted to by clicking round, this, putting in comma, 1 for 1 decimal, 2 for 2 decimals, 3 for 3 decimals, blah, blah, blah. So, let's check out a couple of word problems. A television transmission tower, 2,000 feet high, supported by guy wires running from the ground to the top. The wires make an angle of 63 degrees with the ground, and we want to find first, how long is each wire, and second, how far from the base of the tower are the wires anchored to the ground. If you're wondering what the heck a guy wire is, this is an example of a guy wire. They're the lines that are going from telephone poles, or in this case, a transmission tower, and they just help anchor it in place. So we want to find how long each wire is and how far from the base they're anchored. And thankfully we have this nice little diagram. If you're ever not given a diagram with one of these, it really, really helps. You might have some difficulty in seeing this one, so I'm going to sketch it out again. We got our tower. We know it's 2,000 feet tall. We got a guy wire. We know it's 63 degrees to the ground. Cool. Now, it's helpful to label everything. How long is each wire? So that's our wire. I'm going to label it A because it's for part A. And then how far from the base of the tower are the wires anchored to the ground? Well, that's going to be my B right here. So that's going to be B. That's going to be A. And I know that I can just go through this by setting up trig ratios and solving it out. So for instance, for A, I know that sine of 63 degrees, let me move this a bit further out of the way. Actually, let's move it all the way out of the way, is equal to 2,000 over whatever the heck A is. Now, that means that A is equal to 2,000 divided by sine of 63 degrees. If you're wondering how that happened, I cross-multiply then divided by sine of 63 degrees. Well, I can plug this into a calculator, and I can get that this is equal to 22 point, oh, excuse me, I miswrote there. I can plug this into a calculator and get that it's equal to 2,244.6524 ... feet. So that guy wire, pretty long. Let's take a look at B. Now, B, you have some options. You can use A that you got, or you can use just the given information. I'm just going to use the given information here, just in case I happen to be off and don't really want to use my thing for A. So in order to solve for B, I'm going to do cosine of 63. That's going to be equal to 2,000 over B. Then, in very, very similar form, and that means that B is going to be equal to about a little over 1,000 feet. We've answered everything. Now, it's always a really good idea to just write these things out in statements. So my answer to A would be the guy wire is about 2,244.7 feet long. Notice I rounded there, I said about. And then B, I can say the wire, or the guy wire, anchors about 1,019.1 feet away from the tower. I've answered everything with it. I've checked. I'm good. Let's check out one where we're using our inverse trig functions. Our volcano problem. Haleakea is a 10,000 foot tall dormant volcano on Maui in Hawaii. The horizontal distance from the peak of the volcano to the ocean is about 30,000 feet. At what angle would you have to look up to see the peak if you were standing on the beach? And what is the straight line distance from the beach to the peak? And this is an example from the National Park Service of the mountain in question. It's rather beautiful. It's actually above the cloud line. You can see that there are clouds over here. So I would love to actually go there one day, but hey, not during a pandemic. Moving on. So we have a diagram here. We got our 10,000 feet. We have our 3,000 feet. We got our peak here. We have our beach. We're asked to find how far. So let's label this out and see what we're doing. So at what angle would you have to look up? That's going to be this angle, A. And then what's the straight line distance? That's going to be this, B. Well, let's find A. In order to find A, I need to set up a trig function. So I'm going to use tangent of, let's call it theta. And that's going to be equal to 10,000 over 30,000. If you wanted to reduce that to 1 over 3, you could. It won't really make that big a difference. I then apply my inverse trig function to both sides. And then plug it into a calculator and solve it out. So that's going to be 18.4349 ... degrees. And this makes sense because I got 10,000 here, I have 30,000 here, so that degree measure would make some sense. Now let's talk about B. There are a couple of different ways you could find B. One way is you could use either of the two side measurements you have, and either sine or cosine to find the hypotenuse. I'm going to take a slightly different approach, and I'm just going to use the Pythagorean theorem. This is a right triangle, so I'm just going to say, take my square root, that equals C, plug it into a calculator, and I'm going to get C is approximately 31,622.7766 feet. And always going to be able to answer these things using a summary statement of sorts. So I can say the angle from the beach to the peak is about 18.4 degrees. I can also then say, for the second one, the straight line distance from the beach to the peak is about 31,622.8 feet. So you've gone and seen how we can use our right triangle problems and enter them into Desmos to get an answer. You've seen the difference between our exact answer with the ellipse and our approximate answer. You've seen how we write summary problems. You've seen how we can use sine, cosine, and tangent to rewrite things that are involving secant, cosecant, and cotangent. So you've seen it all. You're good to go. Now, head over to Delta Math if you're not there already, and you're going to do those 10 problems. 5 are finding a side, 5 are finding an angle. And then you have 4 problems from your textbook, as well as the Q questions. Q questions are just 10 minutes. If you have any questions, ask on the Zoom call, or see me during office hours. And have a great day, folks.